So, in this lecture I am going to discuss a little bit about the nature and the stability of the critical points. This will be a short lecture that will summarize some of the things that we illustrated in the last two lectures. Okay. So, before I do that, I just wanted to mention a few things. I had a few things to the last lecture. The first thing is if you remember, in the last lecture we had done all these we had looked at the phase space picture of the pendulum, okay, and we had found that the critical points, okay, so there is a critical point at 0 and a critical point at pi, and what we found is that the trajectories near the critical point at pi, they actually go in this form. Okay, so they go in this way. So they do not go to the critical point at pi or 3 pi, okay, but they go away from this. Now there is just some terminology. We called these points, the 0, 2 pi, etc. These we call them as centers. Okay, these are called centers. Okay, because the trajectories never approach this. Okay, they are centered. They are periodic orbits around this center. Okay. Whereas these pi, 3 pi, etc. So these are actually what are referred to as saddles. We will see exactly how you define them. Okay. So this is called a saddle, and there is a good reason for calling it a saddle. Okay. It has to do with the eigenvalues and eigenvectors. Okay. Now the other point I wanted to make was regarding this separatrix. So in the separatrix you have C equal to omega square. So you can ask the question, what is the equation of this separatrix? So what is the equation of separatrix? So the equation of separatrix, okay, so you go back to our original equation. Okay, so we have this omega equal to square root of 2 c plus omega square cos square theta. Now c equal to omega square, okay, then I can take I can write omega square plus omega square cos theta, and I can take it outside the square root. Okay, so I have omega equal to square root of 2 omega, and you have 1 plus cos theta raised to half. And if you use the trigonometric relation for cos theta, okay, then you can show that cos theta is 2 cos square of theta by 2. Okay, so I can take the square root of 2 and multiply it by this. I will get 2 omega cosine of theta by 2. This is the equation of the separatrix, and you can see that it looks like a cosine function with a period of in fact the period is 4 pi, not 2 pi, because you have theta by 2. Okay. So this is nothing but this equation of this separatrix is omega equal to 2 cos, or 2 times this omega, which is a constant, cos theta by 2. Okay. So the amplitude right here is just 2 omega. This is the equation of the separatrix, and we can actually find that equation. Okay. Now let us go to the main topic for today, that is the stability of the critical points. Okay. And this as I said will be a summary of what we have done in the last couple of lectures. Okay. So remember, in the last lecture we started with this differential equation, and we said it is a second order differential equation, and we can write it in general as f of x dot. We can write this as x dot equal to y and y dot equal to f of x y. So this is a general nonlinear differential equation. Okay. And what we said is that you linearize this nonlinear function about the critical point. So this is not, so f of x y is basically nonlinear. So it might contain terms like x square or y square or x into y and so on. So when you linearize about the critical point, then your f of x y becomes this form: ax plus by. A and b are scalars or constants. Okay. So now this becomes a linear system, and I can write this as V dot equal to 0 a 1 b into V, where V is basically x y. So when I linearize about the critical point, remember linearizing involves a Taylor expansion, okay, some sort of expansion. Okay. So that is you have to keep that in mind. Now once you have a linear system, okay, then you know that the solutions have this form. Okay. So solutions look like e to the lambda t, okay, where lambda is an eigenvalue of A. So in general this eigenvalue of A is written as a real part plus an imaginary part. So in general it is complex, okay, and since it is complex I can write it as lambda real plus I lambda times lambda imaginary. So this is the imaginary part and this is the real part, and I is the unit imaginary number, okay. And now you and more additionally you have two eigenvalues. So lambda 1 and lambda 2, and each has real and imaginary part, each has a real and an imaginary part, okay. It is possible that the real part might be 0, possible that the imaginary part might be 0, okay, but in general each has a real and an imaginary part, okay. Now let us look at some cases, okay. Now if lambda r is less than 0 for both lambda 1 and lambda 2, okay, lambda r is less than 0 for both lambda 1 and lambda 2, okay, then we say that the critical point is asymptotically stable. That means the trajectories, they approach the critical point as t tends to infinity, okay. So as t goes to infinity, the trajectories will go towards the critical point, okay. So such a critical point is said to be asymptotically stable, okay. Now there are several cases which we will also look into in more detail, but generally if the real part is less than 0 for both lambda 1 and lambda 2, then the important thing is it is stable. That means your trajectories will tend towards the critical point. That means if you go to very large time, then you will end up at the critical point, okay. Now if on the other hand if the real part is 0, okay, if the real part is 0 and if the real part is 0 for lambda 1, it has to be 0 for lambda 2 also, okay. That means the both lambda 1 and lambda 2 are purely imaginary, okay. If they are purely imaginary, okay, then we say that the critical point is stable, okay, and the solution is oscillatory. Solution is purely oscillatory, so you will just get an oscillating solution, but the critical point is stable in the sense that you do not have any trajectories do not approach critical point as t tends to infinity, but they do not go to infinity. The trajectories do not diverge away and go all the way to infinity as t tends to infinity, okay. So this is the case what we did in the so this, for example, all these 0, 2 pi, these are examples of stable critical points where the trajectories are periodic around it, okay. The eigenvalues are purely imaginary, okay. Now the third case is if the real part is greater than 0 for either lambda 1 or lambda 2. See, if the real part of either lambda 1 or lambda 2 is greater than 0. So this could happen in two ways. It could be that both lambda 1 and lambda 2 are real, okay. So both are real, but one of them is greater than 0, one of them is less than 0. That is one possibility. The other possibility is that lambda 1 and lambda 2 are complex. If they are complex, then they have to be complex conjugates of each other, okay, but their real part is greater than 0. In this case the critical point is unstable, the trajectories go to infinity as t tends to infinity, okay. This is the, I mean we are just looking at the in the vicinity of the critical point, and that would be this pi and 2 pi are examples of such critical point, because you see what happens to the trajectories, they go away from this, okay, and they diverge all the way, at least in the linear limit they diverge away from that critical point, okay. So these are the nature of the critical points, okay. So what we have said is we have basically said whether they are stable or unstable, okay. And this is a very important thing to know, okay. When you are analyzing nonlinear differential equations, you want to know you want to know which are the stable and unstable critical points. There is a more there is a broader classification of critical points, Okay. And I will just mention this terminology, okay, and you can actually work out examples of each of these. Okay. We will do it during the practice problems. So, the terminology of critical points, you can refer to them as stable or unstable. This is based on the sign of the real part. Okay. So, that is just what we saw here. We saw the real part is either less than 0, then it is stable, equal to 0, then it is stable, okay, and if it is greater than 0, then it is unstable. So, that is one part. The second part is we talked about saddle and spiral and center. We saw these kind of critical points, okay, and if you remember the spiral point, okay, I can show you from the last lecture. Okay. So, what was the spiral point? Yeah. So, this is an example of the spiral point, okay, which we saw in the case of the damped harmonic oscillator. Okay. So, this critical point is a spiral point. What is important is that each of these can be characterized. Now this is what we called a node, a stable node. Okay. So, this is a node because all trajectories go towards that node. Okay. So, we also saw this other terminology where you have nodes and spirals and we call this is a center, this is a saddle. Okay. So, there are centers, saddles, nodes and spirals. Okay. Now, these are actually related to the sign of the real and imaginary parts. So, if you have critical points, there are various possibilities. You can have lambda 1, the eigenvalues lambda 1 and lambda 2 are not equal to each other, but both are real and both are positive. Okay. Then you will get a node, okay, and you can easily tell that it will be unstable. Okay. But the point is, this is a node, and a node, remember, in a node what happens is that all the trajectories either go to the node if it is stable, or they go away from the node if it is unstable. So, if they are positive, then your critical point and all the trajectories go away from the node, okay, and they can go in various ways. They can go either straight or they can go in curves. Okay. But the point is, they go away from the node, and in this case lambda 1 and lambda 2 are not equal to each other, both are real, both are negative. Now, that is also a node, okay, and in this case it is a stable node. Okay. So, since they are negative, it is a stable node. If they are both real, one positive and one negative, okay, if lambda 1 and lambda 2 are both real, but one is positive and one is negative, then you get the saddle point. If lambda 1 is equal to lambda 2 and both are positive, okay, then, or if lambda 1 is equal to lambda 2 and both are negative, in both these cases you get a node, okay, and it is actually a slightly different kind of node. Okay. This is what is called a proper node. Okay. But again, it can be either stable or unstable. Okay. So, in this case, if both are negative, then it will be a stable, in this case it will be unstable. Now, if lambda 1 and lambda 2 are complex, okay, such that the real part is greater than 0, then you get a spiral. If they are complex where the real part is less than 0, you also get a spiral. And if lambda 1 and lambda 2 are purely imaginary, then you get a center. Okay. Again the spiral can be either stable or unstable. So, if it is you could have a spiral where trajectories go into this they go to the node, okay, or they can go away from the node. So, you could have a spiral where the trajectories they start at the node and they go away from the node, or you could have a spiral, okay, in which case the trajectories you could have a stable spiral where the trajectories go and into the node. So, they go from outside and they approach the node. Both these are possible, okay, and again the stability or instability depends on the sign of lambda r. Okay. And the last thing is, if lambda 1 and lambda 2 are both imaginary, then it is a center. Okay. And center is considered a stable point, okay, even though the trajectories do not approach that point. So, these are the various kinds of critical points, okay, and what we will do is to look through examples how we use this, how we identify the behavior of the system by identifying these various critical points. So, in the next lecture we will look at some of these critical points. Thank you.